Hello, welcome back to AP Calculus. We're in Unit 4 right now, which is all about advanced differentiation techniques, particularly the technique of implicit differentiation. We are currently studying related rates, which are a problem type that can be solved using the implicit differentiation technique. In this lesson, Lesson 5, I want to focus on related rate problems that involve angles. Problems with angles sometimes trip up calculus students, but if you practice and you look for patterns, I think you can find an easy way to solve these problems. So, that being said, let's dive right in. An old man casts his line into the sea. While holding the tip of his pole at a constant height of 5 feet above the sea, the old man starts to reel in his lure from the sea. He reels in the line at a constant rate of 1 foot of line per second. What is the rate of change in the angle the line makes with the water when there is 13 feet of line out? All right, so what's happening is the fishing pole is going to be at a constant height of 5 feet. That is not going to change. And we're going to be reeling in the line. And so this length here, the length of the line, is going to change. And this, the length of the horizontal distance to where the line enters the water, is also going to change. And we're looking for the rate of change in the angle the line makes with the water. So that's right here. Well, I'm going to call this X and this Z, staying with my kind of common doing of X left and right, Y up and down, and Z on the hypotenuse. All right, so what we want to do when we're looking for an angle is we need a right triangle. And if we have any constant quantities, we want to try and include those in a trig ratio. Then we want to also include a side length that we know the rate of change of, because that's the variable that we're going to take a derivative of. So let's look at the problem and see what we're told. Well, we're told that he reels in the line at a constant rate of 1 foot of line per second. So, since we know that the line is being reeled in that way, we know dz dt, z is getting smaller, so that's going to be a negative 1. So we want to use z because we know the rate of change in z, and we want to use 5 because this rate of change is constant. If we used x, we then have to solve a totally secondary problem to find the rate of change in x first, just so we can solve the original one. And we don't want to do that. So we need to think of a ratio from sine, cosine, tangent, secant, cosecant, cotangent that involves 5 and z in relation to theta. Well, 5 is the opposite leg, and z is the hypotenuse. And so hopefully you remember that from SOHCAHTOA, sine is opposite over hypotenuse. Now, I hope I didn't confuse you there with the word SOHCAHTOA. That's just kind of an old school little rhyme there. SOHCAHTOA. For sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Just kind of a nonsense word, but for some reason it sticks in your memory and it reminds you of the ratios. All right, well, let's take the derivative here. Well, I think I'm going to say sine of theta is equal to 5 times z to the negative 1. I'll rewrite it like that. And we're going to take the derivative with respect to t. So the derivative of sine u is cosine u prime. So now I have to take the derivative of theta with respect to t. So d theta dt, which is actually what we're looking for in this problem. Then on this other side, I get negative 5z to the negative 2 times dz dt. Okay, well, let's figure out what we know. We know quite a bit here. We know that z is 13. And I'll just make that 13 squared on the bottom since it's a negative 2. We know that dz dt is a negative 1. But how are we going to figure out what cosine of theta is? Well, kind of a rookie mistake here would be to think you would need a calculator and you'd have to actually, figure out and calculate using arc cosine or something like that. But we really don't, because we're told that at the instance when there's 13 feet of line out. Well, let's take a look at that triangle in particular. So this is 5. When there's 13 feet of line out, again, we've got a Pythagorean triple. That's 5, 12, 13. Well, the cosine of theta at this moment is a ratio of side lengths. I may not know what the angle theta is, but I know the cosine of it is the ratio 12 over 13. So that's the cosine of theta right there. Okay, so the -5 and -1 make a +5. And I'm going to multiply both sides by, show it a different color here, by the reciprocal of 12 13. So I'll multiply by 13 twelfths. Okay, so the 13 will reduce to a 13 to the first. Okay, so 13 times 12 then is 156, I believe. Oh, still in. There we go, 156. So that is d theta dt. Well, let's talk about the units. Well, we can do some unit analysis here. We have 5 feet times 1 foot per second divided by 13 feet squared. So that is feet times feet over feet squared. All we have left in the 2 feet on top are canceled out. All we have left is per second. What? How could we not have like feet? Because you remember this was 5 feet and this was 1 feet per second, and feet squared, and that's 13 feet squared. So we just have per second. Well, the units are a rate of change in an angle. So what we're saying is the angle is increasing by 156 radians per second. And you don't actually have to say the word radian. You could just say per second. Radians are a unitless measure. We just call them radians because we just kind of like to, but they're unitless measure. So really, the angle is changing by 156 per second. That's the actually correct units. Does it make sense that the angle would be increasing? I always want to be looking at that. Well, as we reel in this line, this is getting smaller. This is getting smaller. This is getting smaller. And can you imagine when that line is in this situation here? Because the 5 is staying constant. That's going to be a much bigger angle. So yeah, that angle should be slowly increasing as this line comes in. So that answer makes sense. All right, let's take a look at another example. A spectator watches a rocket lift off from the ground from a distance of 5,000 meters from the launch pad. When the rocket is 12,000 meters in altitude, I should say it is lifting off at a rate of 8,000 meters per second. Assuming this situation can be modeled with the right triangle, that's a very big assumption, right? Describe the rate of change in the angle of elevation from the viewer to the rocket. All right, let's take a look. So we have this right triangle here. Theta. The viewer is a constant 5,000 meters from the launch pad, right? And then as the rocket goes up, this angle is going to get bigger, right? So I'm going to call this, sticking with our convention, y, and this z. So I need a ratio. Well, what are we given? We're given that at a certain moment, it's lifting off at 8,000 meters per second. So we were actually given dy dt at that moment. We're not saying that that's a constant dy dt, but it is at that specific moment. They say it's what it is, meters per second. So remember the rule is we want to use a constant if we can. If we can't, then we can't. But we want to use a constant if we can, and we want to use the side length that we are given a rate of change for. So I want to use 5 and 5,000. Well, that's an opposite leg and an adjacent leg. So that tells me I should be saying the tangent of theta is equal to y over 5,000. Now the derivative of tangent u is secant squared u prime. And the derivative of y is 1 times dy dt. All right, well, let's figure out everything we need to know. We already know that dy dt is 8,000. We need to find d theta dt, the rate of change in the angle. But I need to find secant squared theta. Well, we just need to use some Pythagorean theorem. So there's theta. I know that this length here is 5,000. I know the height here is at that moment 12,000. That is a 5, 12, 13 multiplied by 100. So this is 1300. And so secant, remember secant is cosine flipped over. Cosine from SOHCAHTOA is adjacent over hypotenuse. So secant must be a hypotenuse over adjacent. And we want to go ahead and reduce that. It's just 13 over 5. So 13 over 5 squared. All right, so that tells me that d theta dt is equal to, let's see here, let me cross out a couple zeros here. I got 80 over 5 times 5 squared over 13 squared. So I'll lose one of these 5s, right? And so that's 400 over 169, and that is in radians per second. So that's a pretty fast change, right? That's a substantial change. Well, look at how far away we are from the launch pad. We're only 5,000 meters away. So it probably wouldn't be that surprising to think that we would have to, crane our neck pretty fast. Of course, it's not going to be constant, right? The higher that goes, we're going to slow down more and more and more. But at this moment, when it's only 12,000 meters up in the air, we're looking, it's going up fast right there at the beginning. All right. Let's take a look at our next problem. Okay, a 6-foot tall person walks at a rate of 5 feet per second toward a 16-foot tall light pole. At what rate is the length of the person's shadow changing when 10 feet from the base of the light? All right, so we've got a 16-foot tall light pole, and we've got a 6-foot tall person. And what's happening is that light is casting a shadow on the ground. And we would know that the person is walking at a rate of 5 feet per second toward the light pole. So if I call this x, then I know that dx dt is actually equal to a negative 5, right? And maybe I could call this y. All right. Well, let's set up a proportion. The big triangle's height is 16. To the little triangle's height is 6, as the big triangle's base of x plus y is to the little triangle base of y. And I'll just do a little cross product here. 16y is equal to 6x plus 6y. So 10y equals 6x. And we can actually go ahead and reduce that even further. We'll just say that y is equal to 3/5 x, right? Y is the length of the shadow. We want to find the rate of change in the length of the shadow. Well, just take the dy dt. And it's equal to 3/5 dx dt. Turns out that the rate of change in the length of the shadow doesn't depend on their location from how far away they are. It's going to be 3/5 times the rate of change of negative 5. So we're going to say negative 3 feet per second. At what rate is the tip of the shadow moving when 10 feet from the base of the light? Okay, that's a slightly different situation here, because here we're talking about, I should point out, by the way, in that last question, we never used the 10 feet away. I mentioned that it's not dependent on x, so we didn't use it. We might need to use it here, though, so we'll wait and see. So the tip of their shadow is this distance of x plus y. So x plus y is the tip of the shadow, right? So let's find the rate of change of this. I'm going to call that, s for shadow. Well, then the position of the shadow is ds dt is equal to dx dt plus dy dt. Oh, well, look at that. We already know dx dt. That's negative 5. And we just found dy dt, that's negative 3. So it's negative 8 feet per second. This is kind of a neat little problem, the lamp pole problem. Depending on how you set it up, either your you're either going to find the rate of change in the shadow's length first and then use that to find the rate of change in the tip of the shadow, or you can find, depending on how you set up x and y, like I could have defined y to be this entire length here instead of just the length of the shadow. Maybe you'll find the length of the rate of change in the position of the shadow tip, but then you can use that, subtracting dx dt, to find the rate of change in the length of the shadow. So the order that you find these two things in, it could be in any order, it's depending on how you set it up, but it's always doable. All right, last one. At what rate does the angle of elevation from the tip of the shadow to the top of the light pole change? Okay, well then that's a different story, right? So we've got the angle of elevation from the tip of the shadow to the top of the light pole. Well, this light pole, do you remember how tall that light pole was? It was 16. That's constant, right? And we found that this light pole, this tip of the shadow is actually, which I'm going to call x, dx dt. I know earlier I called it x and or ds or something like that. But I usually call this x, y, and z. Oh, well, fine. I'll call it s. Might as well be consistent, right? So that's s. Well, we found in the previous problem that the ds dt is equal to a negative 8 feet per second. So we want to use this constant. We want to use this length here. So I'm going to say, well, I could say tangent of theta. Tangent is opposite over adjacent, but I'm going to say cotangent of theta is equal to adjacent over opposite. That way, I don't have to get like a negative power, right? So the s will go away. So kind of a trick to use the reciprocal sometimes. Because if I use tangent, then I'm going to have 16 over s, which means I get negative 16 over s squared when I take the derivative. All right, the derivative of cotangent is negative cosecant squared theta d theta dt. And this is 1 over 16 times ds dt. All right, well, what is it? We need to figure this out. At this, we don't have that rate, do we? Because we need to know it at a specific moment. Oh, you know what? They must mean 10 feet, right? Yeah, when 10 feet away. Sorry about that. When 10 feet away. So that is when the shadow moving when 10 feet from the base of the light. So the person, let's try, that's the person is 10 feet away. So 16, and that is 10. Oh, no, wait, sorry. That is 6, and he's 10 feet away. So we could solve this little algebra problem here. We've got 6 is to x as 16 is to 10 plus x. All right, so we avoided having to solve this whole time, but now we got to do it, right? Because the short triangle is 6, and the base is x. The big triangle is 16 for the height, and then the base is 10 plus x. And you could set this up in several different ways. So 60 plus 6x equals 16x. So 60 equals 10x. So x equals 6. Oh, yeah, of course, because that would be 16 to 16. Okay, makes sense. So, if x is 6, then this entire length here is 16. Which means that this length here is, well, you would have to use the Pythagorean theorem. If you notice that this is a 45, 45, 90 right triangle, you could actually tell you what angle this is. That angle has to be a pi over 4 angle, right? So this is just really the cosecant squared of pi over 4. Maybe you could just figure that out. If you don't know that, you could realize that this ends up being 16 root 2. Or you could say it's the square root of 16 squared plus 16 squared. Right? This which is perfectly fine, because watch what's going to happen. We're going to have negative, the cosecant is cosecant is sine flipped over, right? Sine is opposite over hypotenuse. So this is hypotenuse over opposite. So this is the square root of 16 squared plus 16 squared over 16. But then that whole thing is squared d theta dt. So the fact that it has a radical in it does not bother me one bit. And then what is this? ds dt, we found out what that was, right? That's negative 8. So this squared is going to cancel that. these two negatives are going to cancel. This is going to be just a 1/2. So this is 16 squared plus 16 squared all over 16 squared. All right. D theta dt. So agree with me, this is 216 squared over 16 squared, so that's just 2. So d theta dt must equal 1. 1 radian per second. And there we have it. Okay. Looks like you have a practice problem. Go ahead and give this fish problem a try. All right, a fish is reeled in at a rate of 2 feet per second from a bridge 16 feet above the water. What rate is the angle between the line and the water changing when there's 20 feet of line out? All right, so that 16 is constant. The 20 feet of line out is not constant, so don't plug that in yet. That's theta. And we know that the fish is reeled in at a rate of 2 feet per second. Well, I guess you could call that a little bit vague. I mean, is it reeled in horizontally 2 feet per second? If that's the way you did it, no big deal. Just, say that's what the problem meant. But I think the problem meant, and if it was, a test question, it would be more clear. But I think it's safe to say, if we call that z and x, that they're telling us that dz dt is a -2. So I want to use z in this situation. Now I could say that this is sine of theta equals 16 over z. I did that earlier. But why don't we try a little differently? Why don't we say instead that the cosecant of theta is equal to z over 16? Yeah, it's just a little different way to do it. Take the derivative. You get negative cosecant theta cotangent theta d theta dt equals 1 over 16 dz dt. All right, so then when I start plugging stuff in, all right, well, we got to figure this out. Well, it said when there's 20 feet of line out. So 16, 20, this is a 3, 4, 5, right? Triangle, so this is everything times 4, though, right? So 3 times 4 is 12, 4 times 4 is 16, 5 times 4 is 20. So cosecant would be hypotenuse over opposite. So that's 20 over 16, which is 5 over 4. So this is a -5 over 4. Cotangent is adjacent over opposite. Remember, it's tangent flipped over. Tangent's opposite over adjacent. So it's 12 over 16, which is 3 over 4. Equals 1 over 16 dz dt. Oh, well, what is dz dt? We better know that, right? Well, that's 2 feet per second, right? Well, a -2 to be exact. All right, so this ends up being a -15 over 16. So if I multiply both sides by a -15 over 16, multiply both sides by, 16 over 15. A -16 over 15. The negatives cancel, the 16s cancel, and we're left with 2 over 15 radians per second. Definitely increasing as you reel it in. All right, let's try the next one. A balloon in the shape of a sphere is inflated at a rate of 24 pi cubic centimeters per second. How fast is the radius of the balloon increasing when the radius is 7 centimeters? Pause the video and give it a try. All right, here we go. A balloon in the shape of a sphere is inflated, so it's increasing with this rate of change in volume. How fast is the radius? Well, we know that volume is 4/3 pi r cubed. So dv dt must be 4 pi r squared dr dt. So I can plug in some stuff here. It's inflating, so dv dt is positive. That's very important to consider. So 24 pi equals 4 pi. When the radius is 7, so r is 7, and we're looking for dr dt. Okay, so let's see here. Pi is going to cancel, and this is going to 24 divided by 6 is 24 divided by 4 is 6, and 7 squared is 49. So we'll just go ahead and divide that. 6 divided by 49 centimeters per second is the rate of change in the radius. Definitely increasing as you increase the balloon. All right, another one, a large block of ice. Pause the video and give it a try. All right, a large block of ice is melting on a table. The ice is losing 2 cubic feet of ice per hour as it melts. Assuming it maintains its cubic shape, big assumption again, how fast is the surface area of the cube changing when the volume is 27? Okay, interesting. Well, let's start with the volume. Volume is s cubed, right? So dv dt is equal to 3s squared ds dt. Well, we know that we're losing 2 cubic feet. So dv dt is -2. And it wants to know when the volume is 27. So I don't know the size, but the side length, but I can solve it. So because volume equals side cubed, so 27 equals side cubed. So side must be the cube root of 27, which happens to be a 3. So 3 squared. And we don't know ds dt, right? We don't know the change in s. So ds dt. All right, well, it's a -2 times, well, this turns out to be 27 again. So it's a -2 over 27 feet per, is it minute? Oh, it's hour. Feet per hour is equal to ds dt. Well, we were asked actually how fast is the surface area changing? Well, remember the area, they gave us that formula as well, is 6s squared. So dA dt, if I take its derivative with respect to time, is 12s ds dt. So dA dt is equal to 12 times s. What was s at this moment? S was 3. And ds dt, we just found, was -2 over 27. All right, well then that makes this, let's see, the 3 can reduce, that's for sure, making that a 9. The 12 is 3 times 4, so that's going to make that a 3. So this becomes a -8 over 3. And this would be feet squared per hour. And again, I'm just going on the fact that it's area and a rate of change, but you could certainly confirm that. We're multiplying we're multiplying s, which is in feet, times feet per hour. So feet times feet is feet squared over per hour. All right, we got another problem to do here. So pause the video and give this one a try. All right, so here we go. Suppose the particle travels along the curve at y equals x squared with a horizontal component of velocity equal to 3 feet per second. When the x coordinate is 2 feet high, 2 feet to the right of the origin, what is the vertical component of the particle's velocity? Okay, let's take a look. When the x coordinate is 2 feet to the right of the origin, that means x equals 2. What is the vertical component? Well, we know that y is equal to x squared. That's the path. So if I take the derivative with respect to time, I get dy dt equals 2x dx dt. So the vertical component of its velocity would be dy dt, because y is vertical. And that must equal to 2 times 2 feet times the rate of change in x, which is 3 feet per second. So that would be 12 feet per second. Kind of an interesting thing here, though. Notice this relationship here, that you can kind of define the parabola as something where the rate of change in the y is going to be twice that of the rate of change in the x times the x value. So we really see that acceleration in the y, that as we move further and further right, we're going to keep doubling over and over and over again that rate of change in y. So it's kind of a neat relationship, I think. All right, at x equals 2 feet, what is the magnitude of the velocity? So the magnitude of velocity is the velocity in the horizontal direction squared plus the magnitude, the velocity in the y direction squared, square rooted. This is actually kind of teetering on a calculus 2 or calculus BC concept, so you probably wouldn't see this question, but I think it's on the AB exam, but I still think it's worthwhile. So if we look at velocity here, here's the velocity. We call this like the Vx, right? So we'll call this the dx dt here, and this is the dy dt. So it's just kind of a different way of noting. You may have seen it v sub x or v sub y. So I think it makes sense. This is just, that squared plus that squared equals this squared. It's just a Pythagorean theorem. So let's find the magnitude of velocity at x equals 2. So we know that it was, let's see here, 3 was the x squared. The y squared we got was 12 squared. So that's 9 plus 144 is the square root of 153. And that is in feet per second. That's the magnitude. All right. At x equals 2, what is the direction angle of the velocity? The direction angle of the velocity is the tangent of dy over dx, which should make sense here. The direction angle is the angle formed with the positive x-axis. So I just need to say, all right, that's fine. The tangent of theta is equal to dy. What was dy? Dy over dy. Oh, look at this. Dy over dx. Just note that. What does that mean? It's dy over dx is dy over dt, and dx is dx over dt, but the dt's cancel out. So we know our dy dt was 12, and we know our dx dt was 3, right? So the tangent of theta is equal to 4. Notice that that's exactly what you would get if you took the dy dx here. Dy dx is 2x, and 2x times 2 is 4. So it's completely related. So our theta must be equal to the arc tangent of 4. I'll let you figure out what that is. That's some decimal, right? You can put it in the calculator if you want. So at x equals 2, what is the rate of change in the direction angle of the particle's velocity? Oh, okay. So the rate of change in the direction angle of the particle's velocity, that's this. So we know that tangent of theta is equal to dy dx. So we could say that secant, we could go ahead and say secant squared theta d theta dt is equal to, we're going to take the derivative here with respect to time. So it would be, what would that be? Well, you'd have to use like the quotient rule, right? You'd have to say dy dt. It's kind of messy, right? So let's see if we can't do something else. Let's see if we can't do something else. Well, we know that the tangent of theta is going to be equal to dy dt over dx dt, right? So the tangent of theta, what was our dy dt? Our dy dt was 2x dx dt. And our dx dt, we'll just put that there. So it turns out that it's simply equal to, the tangent of theta is equal to 2x, which gives me secant squared theta d theta dt is equal to 2 dx dt. So when x is equal to 2, well, what was the tangent of theta? Was 12 over 13, right? So theta is opposite, tangent is opposite, right? Over opposite over adjacent. So that makes this 9 plus 144. We said that was the square root of 153. So the secant squared theta is hypotenuse over adjacent squared. So that's 153 over 9 times d theta dt is equal to 2 times dx dt was 2, so 4. So our d theta dt must be equal to 36 over 153 d theta dt. Oh, sorry. 36 over 153 radians per, what did we say that was? Second? Radians per second, I think. Yeah. All right, and there we have it. So it's interesting how that works out, isn't it? With the d theta, the x's dt's cancel out and all that. Okay, so that's it for this lesson, and then until I see you again, take care.